So, in this video, I want to talk about the introduction to the first part of the calculus that we are going to do, which is derivatives. Now, I want to specifically get across the idea of what a derivative is to you, and I also want to do a derivative numerically, and I kind of want to show you two different approaches to this kind of process. They're going to be very similar. So the first thing I want to talk about is, again, what is a derivative? Well, a derivative is written several different ways. One of the most common ways to write it is dy over dx. Now, what that's representing is the difference in y divided by the difference in x. And hopefully you recognize that is trying to get at the idea of slope. So now that I've mentioned what we write the derivative as, I'm going to write down one of the common formulas for it. So I'm going to write it as the limit as b goes to a of f of b minus f of a over b minus a. Now notice this f of b minus f of a is actually trying to say one of the y values minus another of the y values divided by the x values. And so this actually is talking about the slope, but what we're doing is we're trying to take one point and get it infinitely close to the other point, to the one we want to find, in this case, point A. Now that I've mentioned that, I'm going to mention that there is another common way that we write this, which is the limit as x approaches a of f of x minus f of a divided by x minus a. And that's going to be the one I use for the second part of the problem, where I try a slightly different approach. So I just wanted to make sure I got that across to you all about kind of my formulation for this. I really use this formula specifically when I'm looking for the derivative at a point, which is what I'm going to do in this first video. So what does the derivative actually tell us? Well, the derivative tells us the slope of the tangent line to the curve. Okay. Another way to think about it is that it actually tells me the slope of the curve at a specific point. So again, you can think of it as essentially being slope. So now I want to kind of flip over and look at my first example here, which is I want to look at y equals x squared minus 2x plus 1 at the point 2 comma 1, which happens to be right here. And I would like to try to find the derivative of this point using this idea of slope. So this is actually a pretty common way to introduce it, and I'm just going to kind of approach this from a numerical limit standpoint. And so numerically, I'm going to make a table, and I'm going to do this in blue real fast. So most importantly, the point that I'm looking at, again, is at 2 comma 1. That's going to be kind of my main point here. So what I want to do is I want to test some points around 2 comma 1, some points on this curve, and see what kind of slope they give me. So for example, I might start here at x equals 1 and say, okay, if x equals 1, what is my y value? Well, in this case, it's 0. So the question is, what happens if I find the slope between 1 comma 0 and 2 comma 1? So that's what I want to do right now, is just kind of see what happens. And notice this is on the left side, and so we'll test numbers on both sides and see what happens. So in this case, let's again say I want to find the slope here. So let's do 1 minus 0 over 2 minus 1. So I'm doing, again, x1, y1, x2, y2, and we're doing y2 minus y1 over x2 minus x1. So 1 minus 0 gives me 1, and 2 minus 1 gives me 1. So the slope between those 2 points is 1 over 1. Now, let me inch a little bit closer to the number 2, okay? Because that's where we're looking at trying to find that tangent line, okay? So, whoops. I didn't mean to get rid of that 1. So let me go a little bit closer, and let's plug in 1.5. If I plug in 1.5 into the function, it's not really visible on my graph, but let me just type this in. 1.5 squared minus 2 times 1.5 plus 1 gives me 1/4, or 0.25. Well, now I want to go ahead and, again, try to find the slope, this time using that new point, 1.5 comma 0.25, and I'm still going to use that 2 comma 1. So I'm still going to do 1 minus 0.25 over the, still using the 2, minus 1.5. Let's see what happens there. If I do 1 minus 0.25, I get 0.75, and 2 minus 1.5 is 0.5. Now I'm going to go ahead and divide that. 0.75 divided by 0.5 gives me a slope of 3 over 2, which is 1.5. Okay, now that I've tried that, I can test one more point over here on the left side. I'm going to pick a really good one. Let's try, for example, let's use 1.9. Let me see what happens if I plug in 1.9 into that original function. So 1.9 squared minus 2 times 1.9 plus 1 gives me 0.81. Okay, so again, we want to find the slope. I'm not going to write that out this time. I'm just going to go ahead and jump right into it. 1 minus 0.81 divided by 2 minus 1.9. Now, when I subtract 1 minus 0.81, I should get 0.19. And when I subtract 2 minus 1.9, I should get 0.1. If I take 0.19 divided by 0.1, I get 1.9. Hopefully, you're recognizing my pattern here. So notice again, in this case, I started off with a slope of 1, then I got 1.5, and now I'm at 1.9. So it looks like if I approach it from the left side, my slope appears to be headed toward 2. So let me go ahead and test some numbers on the other side. So instead of looking at the left side of 2, let's start at 3, okay, and work our way towards 2. So I'm just going to come down here. And let's say I'm going to go ahead and test. Let's also do 2.5, and let's also do 2.1, just to verify and make sure everything's working out nicely. Okay, so if I plug in 3 into the original function, let's see again, 3 squared minus 2 times 3 plus 1 is going to give me 4. While I'm at it, I'll go ahead and plug in the others. 2.5 gives me 9/4, which is 2.25. And if I plug in 2.1, let's see, handy dandy little calculator, we get 1.21. Okay, so let's again plug these into my slope formula. I'm not even going to write these down at this point. I'm just going to kind of show my work here. So we're going to do 1 minus 1.21 over 2 minus 2.1. That's going to be for this first one. We'll do 1 minus 2.25 over 2 minus 2.5, and I'm going to scroll down just a little bit. And for the last one, we're going to do 1 minus 4 over 2 minus 3. All right, so 1 minus 1.21 gives me negative 0.21. 2 minus 2.1 gives me negative 0.1. If I divide those, negative 0.21 divided by negative 0.1 gives me positive 2.1. So there's that slope. Let me go ahead and again check these others just to be on the safe side. So again, I'll just kind of skip to it. 1 minus 4 over 2 minus 3 gives me a positive 3 as my slope. And 1 minus 2.25 divided by 2 minus 2.5 gives me a slope of 5 over 2, which is 2.5. So again, if I'm following this limit correctly, and again, I'm going to draw my little dotted line there. From the left side, we went from 1 to 1.5 to 1.9, which looks like it's headed toward 2. On the right side, we have 3, we have 2.5, and we have 2.1. Also looks like it's headed toward 2. So I feel like at a safe place in this at this time that dy dx at x equals 2 is 2. Okay, so notice again, I'm saying that the derivative of y, the derivative of this function with respect to x, is equal to 2. Okay, now that's one way, again, just to read this dy dx. It's the derivative of y with respect to x. Now, I did want to mention, again, there is a slightly different method using this other formula that I wrote here, okay? Now, I'm going to show this formula a little bit differently, and it's not going to involve the numerical method. It's going to be a little bit more algebraic in this sense. But again, I'm only going to use this formula that I'm writing here when I want to find the derivative at a particular point. That's not going to be something we do all the time, but I'm going to use it this time. Okay, so f of x is the original function. So I'm going to plug that in. I'm going to write x squared minus 2x plus 1. And f of a, in this case, is f of 2. I want to actually find out what the y value is at 2. Well, the good thing is it gives it to me, so I'm going to write minus 1 there. Okay. I'm going to divide by x, the variable, minus a, which is my x value. So notice again, a is 2, f of a is 1. Okay. Now that I've got this written down, I'm going to go ahead and try to do a little bit of algebra up here in the top. Notice we've got x squared minus 2x plus 1 minus 1. So those plus 1 and minus 1 will cancel. We're going to get x squared minus 2x. Whoop, I forgot to write my limit down. I should write my limit down first. The limit as x approaches 2 of, and again, I'm going to go ahead and cancel out those 1s. So we're going to have x squared minus 2x over x minus 2. I'm going to go ahead and keep going. The limit as x approaches 2, and I can factor that numerator, x squared minus 2x. I can take out an x, which leaves me with x minus 2 over x minus 2. Hopefully you see where I'm going with this. The x minus 2's should cancel out. We have the limit as x approaches 2 of just an x left over, which gives me an answer of 2. Notice I got the same answer both times, so I'm very happy. Again, I'm looking for the derivative at x equals 2, and I got the answer of 2. Notice I did once numerically, and I did once using some algebraic limits. Hopefully this helps, because in the next lesson, I'm going to kind of expand the idea of derivatives to not just one point, but to all the points. All right, so keep that in mind as we go to the next video.